This is Dr. Hawkins again, and today I want to talk about Karnaugh maps. We're going to start off dealing with three variable Karnaugh maps. Now we've talked about truth tables before. Here's an example of a truth table in three variables. In three variables in binary, you can count from 0 to 7, or there's 8 possible outputs. And I've put some Y values in there, output values, so that we can work an example here. The Karnaugh map looks like this. You notice it also has the ABC inputs. The zeros and the ones designate their values, so they correspond directly to the positions on the truth table. And then the 8 boxes here are your 8 Y outputs. But they're a little different in the way they're ordered. If you can see, it's going to be a visual thing we'll look at in just a minute. Each one of these boxes corresponds to one of these 8 positions of the truth table. Now, let's look at A first. Input A. Everywhere that A is 0, that's these two positions, these two columns, we call that region not A, or A not. Didn't mean to do that in red. That'll be okay. Let's go back to black for now. We're going to do red in a minute. Anyway, that is A not. Everywhere that A is 1, that's the other two columns, we're going to call that A, the A region. And I want you to notice that we're not going in direct order here. The direct order would be 0, which we have, and then 1, which we have, and then 2 would be next. But we skip 2 and do 3 and put 2 at the end. So this is 0, 2, this is 0, 1, 3, 2 going across the top. The reason for that, this is what we call a gray code. And we've talked about gray codes before. A gray code means when I move from one position to the next, I only change one digit. So I'm going to 0 to 1. Get my pointer back. 0 to 1. I only change the right-hand digit. The 0 stays the same. Going from 1 to 3, I only change the left-hand digit. It goes from 0 to 1. And going from 3 to 2, I only change the right-hand digit. So that's part of what makes up the Karnaugh map. It has those gray codes built in. And as you're going to see in a minute, that's going to allow us to group some of these outputs together and to come up with a simplified, or as simple as possible, Boolean algebraic expression that we can turn into a ladder logic diagram or a digital gate logic, whatever we want to do with it to implement it in hardware and software. But anyway, continuing on with what we were doing, I'm going to do B across the bottom just because there's not a lot of room on top there. Everywhere that B is 1, and that's the two middle columns, we're going to call that B. And then everywhere B is 0, that's the left and right hand columns, we're going to call that B naught. Everywhere that C is 1, we're going to call that C, that's the bottom row. And everywhere that C is 0, the top row, we'll call that C naught. Now, this is a 3 variable. We can also do a 4 variable map. which we'll get to soon. Um, and it'll have CD going down, so it'll be a square. It'll have 16 blocks. We'll look at that shortly. But it'll also use a gray code going down vertically, 0, 0, 0, 1, 1, 1, 1, 0. So you'll have 4 rows and 4 columns in that map. But we'll get there as time goes on here. So let's go ahead and let's fill in the map. We can copy our output values from our truth table into our Karnaugh map. Now each one of these squares correspond to one of those positions in the truth table. I'm going to do this with typing. It takes a little longer, but it's a little neater. And it will make what I'm going to do next a little more easier to see. All right, my top left corner is 0, 0, 0, 0. See, I got 0, 0 on A and B. I got 0 on C, so that corresponds to row 0, 0, 0. And my output for that position is a 0. Change my font from where I did my title. Hang on a second. That's going to be too big. So about an 18 ought to do it. So actually it's supposed to be a 0, isn't it? Try to get it centered in there best I can. It's hard to do with the mouse thing there. All right, that's close enough for this. All right, the next position going down, right below that, is A0, B0, C1, so that's my next row, 1. It also happens to be a 0. Put that in there. These aren't going to be perfect since I'm doing it on the fly, but we get this. I don't know why that changed fonts on me again. It's okay for what we're doing. It's not a big deal. The next one, 0, 1, 0, that's the next row to the right, and it has y equals 1. There we go. So that's my second column, top row. Next row is 3, it's 0, 1, 1, so that's going to be the one right below that one. It is a 0. All right, now we skip a column because the next one, 4, is 1, 0, 0, so that's the far right column in the top row, and its output is 1. The next one, all the rest of them happen to be 1s. I can just fill them all in, but the next row is 5. That's going to be 1, 0, 1, so that's the one right below that. And again, it's also a 1. And then my last 2 rows in the truth table are the remaining third column, where A and B are both 1. This is my 6, my next to the bottom row in the truth table. And then my last one, of course, is 7. That messed up, so let's do that again. All right, we've got our Karnaugh map filled in. And now what we do is we look for groupings of ones. We want to find groupings of 2 or groupings of 4. Every one in the truth table has to be included in a grouping. A grouping can be a horizontal row, a vertical column, or a square. We do have, in this particular Karnaugh map, we have a square of 4 on the right half, and that's where I want to use my red color. We circle those, and we call that M1. But that still leaves a 1 out. Now we can overlap groupings. There's no group of 4 that I can fit that remaining 1 into, but I can fit it into a grouping of 2. And let's use green for that one. We'll call that M2. The M stands for min terms. Let's look at M1 first. Let's look at that grouping of 4. It is in, it's in A, and it's not in A naught. It is in both B and B naught. See, there's some part of it's in B, part of it's in B naught. I'm my pointer again. It's all in A here. None of it's in A naught. But part of it's in B, part of it's in B naught. Now, when it's in both of them, B and B naught, that means there's not a B component to this min term. When it's in one or the other, then there's a component. This one's in A and not in B. And if you look, it's in both C and C naught also. See, there's C naught and there's C. So part of my min terms in both. So it. So we exclude the ones that it's in both the naught and the non-naught, like B and B naught, C and C naught. So this particular min term is simply equal to A naught. All right, now let's look at M2. I'm getting tight on space here, so bear with me. M2 is the green one here. I should have wrote it in green. Not that it really matters. The colors are just helping you identify try to help you identify what I'm doing here. So let's look at this one. You can see part of it's an A, part of it's an A knot. Now, all of it's in C, none of it's in C knot. All of it's in C knot, rather, none of it's in C. And all of it's in B. Would be a knot, not a nut. And B knot. So the bottom two here, it's in one or the other. It's not in both C and C knot. Then we exclude the C. But here it's in C knot, not in C. It's in B, not in B knot. So this min term is going to be B, C knot. So since I only had two min terms, each min term is going to be the product or the and of the letters that make it up. And then we take all the min terms, ever how many we have. In this case, we had two. Sometimes we might have 3, 4, or 5. But my y output's going to be the sum of the min terms, or the OR of the min terms. Y, in this case, we'll do that back in black now. Or we'll have to continue on the next page, it looks like, but it's going to be A knot or B C knot. Now that's a fairly simple expression. And if I wanted to implement that in ladder logic, how would I do that? Well, we're going to have an OR, and remember OR is a parallel combination, AND is a series combination, NOT is a normally closed contact, and then a NOT is a normally open contact. So we're going to have, because it's OR, there's going to be two in parallel. The top branch is just going to have A knot. And I don't write the knot there because the normally closed contact takes care of that for me. And then OR that with B, which is normally open since it's not inverted, and series gives me the and. Remember, it's been a while since we've done this, so I want to go ahead and make sure and throw this in. C knot. And this is my output Y. So that would be a ladder logic function that implements the truth table we looked at on the previous page. Now, I didn't show you every possible combination of groupings that we could have. I do want to do just a couple of more. I'm not going to do a whole other example, but I will show you how some of these groupings can work that we hadn't looked at yet. We showed a horizontal row of 2 in the previous example, and we showed a square on the right half side. There's a couple other ways we could have groupings. Let's pull out another Karnaugh map here somewhere. I wonder where I hit it. There it is. All right. And I'm not going to take the time to be neat with it like I was with the ones. I'm just going to write them in with my stylus, which is a little more messy. But let's suppose I have 1, 1, 1, 1, and the rest zeros. I can have a grouping that looks like this. That one may not be obvious. That's why I want to be sure and explain it. We can have a grouping that looks like that. When we get to the 4 input variables, we can have the 4 corners be one grouping. We'll look at that in the next podcast. We could also have, suppose I had a row of 1s all the way across the top or the bottom row, either one, it doesn't matter. And all the rest of them don't have to be zeros. I'm saying there could be maybe another 1 here, for example, and the rest zeros. Then I would group these like this. That is a grouping, and that is a grouping. This one here, notice that it is all in A naught. Part of it's in C, part of it's in C naught, part of it's in B, part of it's in B naught. Oh, A and A naught, but all of it is in B naught. So this M anytime you have a 4 grouping in the 3 variable input, you're going to get it down to 1 letter for that min term. But if you have a 2 grouping, it's going to be 3 letters, or 2 letters rather. Let's look at the one on the right now. The top row is all in C naught. Notice that that grouping is in A and A naught, B and B naught. So we exclude those 2 variables since it's in both the inverted and non-inverted, but it's all in C naught. So this one will be, if this is top one is M1, it's just going to be C naught. Now the other grouping we had to use to get that bottom one, it's only a grouping of 2. There's no way we can get a grouping of 4 there. So it's going to have 2 variables to it. Notice that it is all in A naught and B, and it's in both C and C naught, so we exclude the C, but it's in A naught and B. So that one's complete output would be C naught or A naught B. This one would just simply be if there's no other ones there. So there's some examples of how you manipulate the Karnaugh map for 3 variables. I'm going to give you a couple of homework problems to do with that. That'll be in a separate item, a separate announcement. that I'll post along with this. Um, and that will be due, let's see, today's Thursday. Let's make that due Monday, because I've got another big assignment I want to do with you on 4 variable maps. So let's get this one out of the way as quick as possible. If you have any questions, be sure and email me, and I'll try to respond and answer them as soon as possible. And look for another posting soon on the 4 variable Karnaugh maps. Have a good day.